Michael Faraday was a great electrochemist, and one of the things that he studied a lot was how electrolytic cells relate to the spontaneity of a reaction. And through a long series of events, this equation was born, where the Gibbs free energy, delta G, equals minus NFE. Now, all of those things have a factor, but I want to talk about F first. F is what they call the Faraday Constant, and it represents 96,485 coulombs per mole of electrons, or if you wanted to use scientific notation, 9.6485 times 10 to the fourth coulombs per mole of electrons. N is the number of moles of electrons transferred. So that'll be something we'll talk about here in a little bit. And if you multiply N and F by the cell potential and put a negative sign in front of it, you're good to go. I highly recommend you memorize / put in your calculator the Faraday constant. We'll use it a lot in this section. That is the last constant you need to memorize. Hint, hint. So that's kind of cool too. But anyway, F is something we'll use a lot. So let's see how you do it. Now, we've already seen that cell potential, if it's positive, that means spontaneous, which means negative delta G. You can see with the negative sign in there, negative will turn the positive E into a negative number. Delta G will be negative. Life is good. Delta G equals minus NFE. If you have a product-favored reactants want to go to products, that means your delta G is going to be negative, less than 0, and your E naught is going to be positive. So that's why cell potentials that are positive, those are the ones that are going to occur. They're going to be product-favored. On the other hand, in a reactant-favored reaction, then products don't really want to form, and their system's kind of stuck on the reactant side. Those are non-spontaneous reactions. Delta G is greater than 0. E naught is going to be negative in those. So every time you have a positive cell potential, that's going to be spontaneous. Delta G is going to happen. On the other hand, negative cell potentials, those are usually dead in the water. Delta G would be positive, non-spontaneous, nothing happens. So let's determine delta G for this reaction, tin 2 plus vanadium going to tin plus vanadium 2 plus, and the cell potential positive 1.07 volts. Now, delta G equals minus NFE, but notice here that cell potential E is a positive number, and a positive number, and F and N will be positive, times a negative there for minus NFE means delta G is going to be a negative number. So the answers here will not be A, B, or C. Those are all positive numbers or 0. It's going to be D or E. Now, cell potential, 1.07 volts, that's E naught. Faraday, 96,485, no problem. N is the moles of electrons transferred. And you can look at either reactants or products like we talked about briefly earlier. I'm going to look at the tin here. Tin is going from a positive 2 to a 0. That means that 2 moles of electrons are transferred per mole of tin 2 plus. You can also look from the vanadium's perspective. V is going from a 0 to a positive 2. That means vanadium is losing 2 electrons. N is the moles of electrons transferred. It's going to be 2 here. So you'd go minus 2 times Faraday times 1.07. You're going to get a really big number. People usually divide by 1,000, turn joules into kilojoules, minus 206 kilojoules here. Notice that delta G initially comes out in joules, so you can turn it into kilojoules pretty readily. No problem. One more thing we're going to do. Sometimes it's nice to know how long a battery will last, or considering how much of a compound you can make. And this introduces an idea of what's called quantitative electrochemistry. Quantitative means how much. So let's say we wanted to turn silver ions into silver metal, and sometimes silver metal is worth a lot. Well, every mole of silver ions need a mole of electrons to make a mole of silver. Well, you can actually figure these kind of things out, but we need to talk about some new kinds of units. And the important one right here is this one right here. I stands for current. So current is I. And current, which is usually measured in amps, an amp is a coulomb per second. Okay, so if I said you had a current of 3.1 amps, you could think about that as 3.1 coulombs per second. A coulomb is a measure of charge. We talked about coulombs briefly in Chem 221. An electron and a proton have so many coulombs. They're the opposite charge. Electrons are negative, positive protons, etc., etc. But just remember here, an amp is a coulomb per second. So knowing that, these problems aren't too bad. In this problem, 1.50 amps, and notice what I did. I right away wrote 1.50 coulombs per second. 1.50 coulombs per second are flowing through a silver plus solution for 15 minutes. And the question is, how much silver metal is going to be deposited? Cool. So what I would do on this problem is start with the time and work my way over into how much mass is there. And I'll show you how this works. We're going to be using the Faraday constant. Remember the Faraday, 96,485 coulombs per mole of electrons. So you can see here I've got minutes. I'm going to turn minutes into seconds so I can use the amps, all right? Coulombs and Coulomb's law, Coulomb's constant, or Faraday constant, excuse me. I can use coulombs, turn them into moles of electrons. And this is silver plus. So you need 1 mole of silver plus to react with 1 mole of electrons to make 1 mole of silver. And from moles, you can go to grams. Let's first of all calculate the charge in coulombs, which means turn your time into seconds and multiply by the amps. So every minute is worth 60 seconds, and we have 15 minutes. And for every second, you have 1.50 coulombs transferred through. So that means in this problem, we have a total of 1,350 coulombs of charge transferred through. Woohoo! Now we have the Faraday constant. We can use those coulombs and the coulombs per mole in order to find how many moles of electrons that represents. 96,045 coulombs per mole of electrons is the Faraday constant. And we have 1350 coulombs. So if you take 1350 divided by the Faraday, you get 0.0140 moles of electrons. All right? That's where the Faraday constant comes in. Now this is silver plus going to silver. It's 1 electron per silver atom that's formed. So if you take that moles of electrons and you realize it's 1-to-1 with silver, then that many moles of electrons represents that many moles of silver. And you can turn it into moles of silver, and you multiply by the molar mass of silver, which is like 107.8, something like that, 1.51 grams of silver. So this is how you do these kind of problems. It's pretty chill. Usually these problems, you start with time and you work to quantity. So that's what we did here. We started with minutes, basically, and worked our way to grams. Some of these problems, you start with grams or moles and you work back to time. Those are the 2 ways that these problems go, and they're both pretty easy as long as you follow these steps. Here's an example of how long something will last, i.e. time, all right? And in this problem, we're starting with quantity, how many grams, and we just want to know how long this battery is going to last. So you're driving out in the desert with your homemade battery. You don't want to have a dead desert in the battery. I guess that's the kind of idea. Anyway, it's kind of the opposite of what we just did. Let's turn grams into moles. So take 454 grams, divide by the molar mass of lead to get the moles. Lead here, you can see, is a 2-electron process. Lead 2 plus is what we have in this battery. So there's 2 electrons per mole of lead. So what we're going to do here is multiply that number by 2. 4.38 moles of electrons are needed for this process. Okay, well, after moles of electrons, we'll use the Faraday constant, 96,485 coulombs per mole of electrons times 4.38 moles of electrons, 423,000 coulombs. Oh, goodness. And then the last thing, if you remember from before, every time you see amp, think coulombs per second. So with 423,000 coulombs, and we have 1.50 amps, which is 1.50 coulombs per second, you want to take coulombs and divide by coulombs per second, or you can take coulombs, and whatever you want to do. Anyway, it comes out to be 282,000 seconds. And because who knows how long that really is, I divided first by 60 to get to minutes, and then I divided again by 60 to get to hours. It's about 78 hours in this case. So your battery would last roughly 78 hours. Cool. Here's a process where we're plating gold, taking gold 3+ ions and turning them into gold metal. And the question is, how long will it take to electrolyze 0.010 moles of gold solution using a 2 amp current? All right. Well, this is a problem where we're starting with quantity and we want to turn it into time. So it's a lot like the lead sample we did earlier. I do this problem because I wanted to show you we have 0.0100 moles of gold 3+, and we need 3 moles of electrons per mole of gold, and that's going to turn gold 3+ into the gold metal. And from there you can use Faraday to find coulombs, and then coulombs per second is what amps is, so you can find seconds and convert if necessary. So here's the math: 2.0 amps, 2.00 coulombs. Because it's gold 3+, you need 3 moles of electrons per mole of gold. That gold 3, of course, is the same 3 as right there. And then once you have mole of electrons, multiply it by coulombs, divide by the amps, or 1 second per 200 coulombs, 1,450 seconds. No big deal.